All right, I want to welcome all of you to the colloquium. It's a great turnout for an illustrious speaker. Renu Malhotra, I think most of you know, but I'll read a little bit of her background anyway. Renu is a Regents Professor and the Louise Foucault Marshall Science Research Professor. Did I say Regents Professor? Did I say that right the first time, or did I say that wrong? Anyway. Regents Professor and Louise Foucault Marshall Science Research Professor at the U of A. She got her master's at the Indian Institute of Technology and her PhD at Cornell. Then after a postdoc at Caltech, did a sojourn at the Lunar and Planetary Institute, where I believe, was it LPI where you're doing some of your the really groundbreaking Pluto stuff? Yeah. And so after figuring out what's going on with Pluto, well, sort of, Renu's interests have moved on farther out, and she's going to be talking to us today about prospects for unseen planets beyond Neptune. Renu.
Thank you, Tim. This is a talk that I put together rather quickly. I'm going to throw a lot of things at you. There's lots of technical stuff behind this this topic, and so let's get started. I hope to get through all the material. There'll be things that I will skip. If you're interested in any particular aspects, I'd be very more than happy to talk to people. There's a lot of work, lots of interesting technical things that this topic has stimulated in recent times. So very briefly, the outline of this talk, I'm going to give you a brief history of the solar system planet discoveries, and I'm going to review the evidence for the currently hypothesized planet X's. So there's a planet 10 and a planet 9. Planet 10 is right here. It's an artist's concept. It's a smallish planet, Mars to Earth size, closer in. So there's you can see the orbit of Jupiter is there. The orbit of Neptune is down there. This one is on the order of about 3 times farther away than Neptune, 2 to 3 times farther away. P9, just to get us on the same page, P9 is much more distant, about 10 to 20 times farther away than Neptune, and also more massive, on the order of Neptune mass out there. So these are the 2 planets that have been hypothesized, and I'll walk you through the evidence for that. But before I do that, let me give you a brief history of the search for planets in the solar system. And this is actually quite a fascinating history in astronomy. So back in the day, going back a couple, 200 years ago or more, humanity, for most of human history, knew of these 7 moving objects in the sky. There's Earth, of course, which wasn't moving at the time, and the other 7. And so we are saddled with a 7-day week. So imagine if they'd known about 10 planets back then. We'd have a 10-day week. We don't want that. Okay. So it was good. We knew only of 7 moving objects, and so these also, we had cosmologies based on these the fixed stars in the background and these 7 moving objects in the sky. And the first planet, really, that was recognized was Uranus, okay, beyond the ancient planets. And this was discovered in 1781. It came about because of new technology, bigger, better telescopes. And this is William and Carolyn Herschel that were credited with this. But there are multiple prior sightings of Uranus recorded previously as a star, and those were then actually people went back and figured out the orbit of this planet better by recognizing that some previous records were also of this object. This was a serendipitous discovery. Okay, so William Herschel pointed his bright, shiny new telescope to the sky and discovered this. The next one, so this, I'd say the biggest consequence of this was opening up human imagination to the idea that there could be more planets, okay? Not just those 7 moving objects we knew about. Okay, so that really, I think, allowed human imagination about planets to imagine, now asking, are there more planets? This couldn't possibly be the last one. There might be others further down, further beyond Uranus. So this is, number of people went furiously working. There were observations of Uranus, and its path was tracked, and it was perceived that its track was not exactly following what would be expected of a planet on an elliptical, fixed elliptical path. And there was a bunch of so there were anomalies in the position of Uranus over even just a few decades, which is quite remarkable. Okay, so Uranus was discovered as a planet in 1791, and in a few decades already, it was realized that this planet was not moving on a Keplerian ellipse. To be fair, this was because we had a longer arc. There were observations of Uranus that we recognized from prior to 1791. So some people, some very strong mathematicians went to work on this. So using mathematics, some amount of guesswork too, Leverrier in particular predicted the location of a possible another planet beyond Uranus, and this led to so he specifically pointed to a particular part of the sky, a position in the sky where this planet was to be found, and marketed his prediction to a few observers, one of whom took him up on it. This was so Neptune was discovered at Berlin Observatory in 1846, and quite significantly, this was also a test of Newton's theory of gravity. Okay, so this was quite a critical test, a more sensitive test of Newton's theory of gravity than previously anything that had been done. Beyond that, what about more planets? So there were anomalies still expected or still discerned in the orbit of Uranus and Neptune beyond what Neptune's discovery could account for. So people thought there could be other planets. And that eventually led to the discovery of Pluto, and that's a long story. Many of you are probably familiar with that. So there were these apparent anomalies in the movements of both Uranus and Neptune, and there were speculations of another massive planet beyond Neptune. The most persistent search for this was led by Percival Lowell, who founded the Lowell Observatory in Flagstaff, just up the road. One historical vignette is this was the first observatory that was put outside of a classical university, okay, an ivory tower. This was the first privately funded observatory. And of course, we know that Clyde Tombaugh discovered Pluto in 1930. And a few decades later, almost 4 decades later, Pluto's moon was discovered, Charon, and that told us very, very firmly that Pluto had a very low mass, on the order of 1/10,000th the mass of Neptune. So it wasn't this expected massive planet beyond Neptune that was thought to be making these anomalous movements. The anomalies were eventually resolved, and the succinct way to put it is that the mass of Neptune had to be revised. We had an erroneous mass of Neptune. This was finally improved after the analysis of the Voyager spacecraft out into the outer solar system. Okay, what about more planets? Okay, so the search hasn't completely died out because we didn't discover, or because we discovered that Pluto is a small planet. The challenge for more planets, for looking for more planets, is that to directly detect a planet, any planet far away would be faint and very slowly moving. Those are the two factors. So distant planets are faint and they're very slowly moving. The slowly moving part is probably the bigger challenge than faint. And as I'll show you, planets like the size of Earth or Neptune, so a few times the Earth's radius, are actually not super faint. They are not anywhere near not being seeable by modern telescopes. The slowly moving part is the bigger challenge. So the current approach is to use distant minor planets as tracer particles. Okay, so to probe for the effects of unseen planets, we use the large numbers of small bodies, the minor planets we have in the solar system, And I'll walk you through what's been done in the last few years, 10 years or so. The story of, or the modern speculations of another planet based on these tracer particles, using minor planets as tracer particles, goes back to at least the early 2000s. And these are some papers if you're interested. So many of these papers have been speculating that there's a massive planet there that's shepherding or perturbing or somehow affecting the structure and the distribution of small bodies in the outer solar system. Most recently, these two papers have stimulated a lot of additional work, a current flurry of activity for both theoretical and observational to look for an additional planet. And what I'm going to do today is walk you through three parts of this. A large planet is going to affect the small bodies in a few different ways, and I'm going to concentrate on these three things. It's going to affect the midplane of the Kuiper belt. Okay, so a large planet, the midplane of small bodies in the solar system is controlled by large bodies, by the massive planets. So is there any hint of that in the midplane of the Kuiper belt? Then there are some hints that the orbits in the outer solar system exhibit an anomalous clustering. They're not randomly distributed, and that clustering is something to do with massive planets. And I'll walk you through some orbital resonance effects. If there is a planet, is it producing any resonant effects that we can see, and how that might help us locate it too. So what do we know about the outer solar system? This is a top-down view. Each little dot here is a minor planet, and the major planets are, they're actually not so easily visible in this, but they are actually marked somewhere. You can actually almost guess where they are. Jupiter is right about there because this is this cluster of Jupiter Trojans. So Jupiter at this present time is located just about there. So that's Jupiter's orbit. This is Neptune's orbit. And all the outer solar system minor planets are these red and white dots. They look like, they look like a bunch of bodies out there. There's some patterns hidden in this distribution. Some of you might be able to tell, even looking at this plot, that this is not uniform. Some of this is observational bias. These red and white dots are not uniformly uniformly distributed in a belt out here. There's some lesser density here compared to here, for example. The white dots are clumps of resonant objects. These are actually Plutinos. They share the same orbit approximately the same orbit as Pluto. So there are some patterns in there. The patterns become more evident when we make these plots of orbital parameters. So what we have here is the same major axis. That's the mean orbital radius. And on the vertical axis, we have two parameters, the orbital eccentricity and the orbital inclination. Okay, so up here, eccentricity means this is a circular orbit down here, and it gets more and more elliptical as you go up this axis. And this is inclination. These are inclinations that are usually in our catalogs. They are reported with reference to a particular choice of reference frame, which is taken as the Earth's orbital plane in the year 2000. It's called the J2000 reference frame. And that's somewhat significant when we talk about midplanes. I'll walk you through why we need to think about what the reference planes are. Okay, so in the shape of the orbit, eccentricities, we can see that there's this pattern that's obvious. And these in orbital parameter space, the Kuiper belt objects are not. We can see some patterns in there. The total number, incidentally, we have is just under 2,000 right now. And what we've discovered is subject to heavy observational biases. So all the orbital parameter distributions are heavily biased. Most of the discoveries are actually closer than 50 astronomical. In other words, right now these objects are closer than 50 astronomical units. Farther away, and they're too faint to be detected, most of them. There are a few that we've seen beyond that distance, and those are actually have garnered a lot of attention. So there's a number of dynamical classes that we've recognized. I've listed these here. There's so-called classical, resonant, scattered, detached, and I should tell you about those. So here's the classical Kuiper belt objects. This is what had been theoretically expected very reasonably that beyond Neptune, if there's any leftovers of planetary formation materials, planetesimals, they would be in a more or less circular and nearly coplanar orbit, so low inclination, low eccentricity. This is what we recognize as that remnant. These are other groupings here that you can see. These are all these vertical magenta lines are places where the orbital period by Kepler's law, by Kepler's third law, is in a resonant ratio with the orbital period of Neptune, which is out here at 30 astronomical units. So these are all orbital resonances with locations of orbital resonances with Neptune. The most prominent one you can see is this resonance here that has lots of the largest number of resonant objects. These are called Plutinos, and they share the orbital period of Pluto. But there are populations in many orbital resonances down here. The next, and then there are these so-called scattered objects. So these lie between these curves here. So these curves represent combination of semi-major axes and eccentricity such that the perihelion distance is common to these orbits. So here the perihelion distance is 26 astronomical units. This is more or less the limit of stability that orbits that have perihelion distance or semi-major axes bigger or beyond Neptune and perihelion distance below 26 AU are unstable under the on short time scales, on time scales of just some tens of orbital periods under the influence of Uranus and Neptune alone. These other lines, perihelion distance of 30 astronomical unit, above that we would have Kuiper belt objects that would be crossing Neptune's orbit, and so unless they are resonant with Neptune, they would be unstable. And there's this lower line, a perihelion distance of 40 astronomical units, that more or less gives us the boundary of Kuiper belt objects that can approach Neptune within about 10 astronomical units at their closest approach to the Sun. And they have very little perturbation by the planets. So when objects are farther than, have perihelion distances greater than about 40 astronomical units, so farther out this way in this region, they cannot approach, they're very little perturbed by the planets. And so these are, and you see a few dots there. So we have some objects there with fairly high eccentricities also. And these have been a puzzle. These are called the detached KBOs. We don't have, KBO astronomers haven't spent a lot of time coming up with nice names for these. So these are pretty unimaginative names. So these are called detached objects. Okay, they are detached in the sense that planets, the known planets, have very little perturbative effects on these. And the boundary is at a semi-major axis bigger than about 50 astronomical units, and perihelion distance somewhere around 35 to 40 astronomical units, and it's a little bit fuzzy, that boundary. It's probably not even a hard boundary, it's a fuzzy boundary in reality, in physical terms. And then there's this population called the extreme Kuiper belt objects, which you can see here. This is in a plot of semi-major axis and perihelion distance now. And the objects that have perihelion distances beyond 40 are thought to be especially detached from the known planets, from perturbations to the known planets. And we'll talk about these in some. Currently we have about a dozen of these known. The two fairly, those that have been, you've probably run into these, they've been in the media some. This is a dwarf planet, Sedna. This is another biggish object. It's not as large as Sedna. This one is called VP colloquially. These are the two most distant objects, but they have some siblings that are also quite far out. And so these are called the extreme KBOs, and they will feature in some of the discussion about planets, unseen planets. Okay, so with that as background, the midplane of the solar system, okay, or the midplane of the Kuiper belt as a probe for distant planets. That's a picture from Alex Parker that you just saw. I really like that picture. It's very evocative. So what do we expect for the midplane of the Kuiper belt. So we have this bunch of minor planets with some dispersion in their orbit, orbital parameters, orbit planes. The solar system, from kindergarten, we learned that the planets rotate around the sun in the same plane, in a common plane. And it's almost true. It's pretty good, to a good degree of accuracy. The planets occupy orbital planes that are very close to each other. This is the Earth's orbital plane, if you look edge on, and the orbital planes of the other planets are only slightly tilted to the Earth's plane. If you take the total angular momentum of the solar system, it's dominated by the angular motion of Jupiter and Saturn, primarily. And that midplane of the solar system is also very close to the Earth's orbital plane, within a degree or so of the Earth's orbital plane. So that's down there. What do we expect for small bodies? So we would expect that small bodies, midplane, is controlled by the planets. How do we measure that? There are two parameters we need to specify an orbital plane. It's how much it's tilted to a reference plane, and which direction that tilt is in, how it's rotated, and that's this nodal angle, big omega. So inclination angle and nodal angle, so two parameters. We can use those two parameters to define a unit vector that's normal to the orbit plane. And that's how we define, how we measure and quantify an orbital plane. And celestial mechanicians for a long time have reduced this to two parameters, a vector which is two-dimensional. We just take the component sin I, sin omega, and sin I, cosine omega, call it a two-dimensional vector, and we call that the inclination vector. So we have two parameters or a two-component vector to define the plane of an orbit. So so what is the theoretical expectation for this midplane? As I said, the midplane is controlled by the gravity of for the Kuiper belt, the gravity of the giant planets. Okay? The Kuiper belt itself has very little mass. Our best estimates are that it's some tiny fraction of an Earth mass. I've put here order of 0.1 Earth mass. Actually, our best estimates are that it's not more than about 4% of an Earth mass. So we can consider the Kuiper belt objects as tracer particles because of this huge mass difference between the giant planets and the entire Kuiper belt. And so if we know what the known planets then tell us what the midplane of the Kuiper belt should be. And that comes from a linearized theory called the Laplace-Lagrange secular perturbation theory. So Laplace and Lagrange in the late 1700s worked this out for the major planets of the solar system to understand how the orbits of the planets change over long times under their mutual gravity. And this is a linearized theory. So basically you think of each planet or each body's mass being spread out on a wire, an elliptical wire, and you ask how those elliptical wires interact, how their mutual gravity affects their shape and orientation over time. So eccentricity and inclination over time. And that's called this secular perturbation theory. This is the basis for things like long-term climate change. Milankovitch cycles come out of this. The reason these guys were doing it was actually asking this very, very weighty question: is the solar system stable over long time? So this is the linearized theory of the solar system. And this theory, if you then say how does a test particle behave under these elliptical massive wires, how does the plane, the orbital plane of a test particle behave? You can decompose that inclination vector that I told you about, that two-component vector. You can decompose it into two parts. One is what we call a forced inclination, and the other part is the free inclination. So this is the inclination vector of a tracer particle, and the forced part is what the planets enforce. And so the inclination of an asteroid, for example, we can decompose it into a part that is forced by the planets, and then there's a free part. So asteroids have a big dispersion of their orbital planes, but on average, so this part is the random part, And this is the part that's common to asteroids, that's forced by the planets. And actually this part varies depending upon where you put your test particle, how big its orbit is. So this is a function of the mean radius, the mean orbital radius of a tracer particle. Okay, so at different mean radii from the sun, you expect different forcings, different average planes based on the planet's orbits. And that's because the planet's orbits aren't strictly coplanar, so they vary over time a little bit. And so if you do this calculation for the outer solar system, so beyond Neptune, this is now in semi-major axes in astronomical units. So Neptune is about here at 30 AU. And this is what we expect for those two parameters, the inclination and that nodal angle at different places in the Kuiper belt, at different mean distances from the sun. So far away, as you go far out from the solar system, this asymptotically reaches the midplane of the solar system, or what you call the invariable plane. This is the plane that's normal to the total angular momentum vector of the solar system, of all the planets. Okay, so that's asymptotic. That is, as you can see from here, that's about 1.5 degrees inclined to the Earth's orbital plane, the Earth's current orbital plane. Okay, so that's how it deviates from the Earth's, or what we call the ecliptic. And then this, there are some, it's not a flat plane. Okay, so there are places where there's a big warp that the planets induce. These are called secular resonances. There are a couple places you can see here. These are places where the planets will force the orbits, the orbital planes of Kuiper belt objects to deviate, the average plane to deviate from the invariable plane. And that happens because the precession frequencies of these tracer particles change with distance. They generally get smaller as you go farther out. But at these places, at these locations, the precession frequency happens to coincide with one of the giant planet precession frequencies. And so it becomes like a forced harmonic oscillator. Remember, it's a linear theory, so there's harmonic oscillators here. And so this is where we have a resonance with the precession frequencies. So, okay, so this is the theoretical expectation. And how do we actually test this, okay, with these tracer particles? Well, we have the observational sample. We want an answer to what is the midplane of this observational sample. Now, the observational sample is not a fair sample of the Kuiper belt. So I'll walk you through a couple of problems that we have. We have to find the right sample, and we also have to be mindful of biases, even in that sample. So for the purpose of measuring the midplane, we want to demand that the orbit be well determined. Okay, this is a particular issue with the Kuiper belt objects because they've been discovered only in the last 20, 25 years. Their orbital periods are hundreds of years long. So we've observed them over only a short part of their orbits. And so the orbits are not super well determined. Okay, so we want to have a sample whose orbits are fairly well determined. So we went through the way we did this exercise. This was done incidentally by Kat Wolk and myself last year. What we did was we said, well, we demand that the orbits be well determined enough that the orbital errors are on the order of 5% or so in semi-major axes and a few other parameters. I won't go through the details of that, just to give you a flavor for this. And then we also identify and discard the resonant objects. Those are a problem because resonances, or objects that are in resonant orbital resonances with Neptune, are not going to obey that secular theory. Okay, those objects will have a midplane or a forced inclination that's not given by that Laplace-Lagrange secular theory, because that's where that theory breaks down. There's some singularities that happen and so on. So we identified and discarded the resonant objects, and then the paired sample then is about half of what we actually, of all the KBOs that we have, about 930 objects. This is their location on the sky in ecliptic latitude and longitude. And you can see that there are some non-uniformities in that paired sample. So the paired sample is still not bias-free. Okay, so these objects have been discovered in many different surveys. Some of these surveys have been systematic, and some have been, many KBOs have been discovered in surveys that were not looking for KBOs, so they were not systematic surveys for KBOs. And I think it's roughly 50-50, the way this is of the sample that we have. And many discovery circumstances are not reported. So we don't know the observational biases super well in these. These are the locations of that paired sample. We can see obvious biases here. These big gaps have to do with the galaxy, because most observations don't look for moving objects where the galaxy crosses the ecliptic. This is the ecliptic here. And the big bias you see is that most detected objects are in the ecliptic, are very close to the ecliptic, because most solar system surveys tend to look at fields that are close to the ecliptic. So how do we find the midplane of this sample? So the naive thing you might think is, so we have the orbits. These are good orbits. These are all objects that we have good orbits for. We know the unit vector normal to the orbit plane. So orbit planes are well known. So let's take the average of all the unit vectors that are normal to the orbit plane. So take the average of this, normalize it, and so on, and find the average plane, the midplane. This turns out to be not a good idea because of these biases. Okay, so very simple bias is that because of the surveys that are concentrated on the ecliptic, the average is going to be biased towards the ecliptic. So we need to do a better job of this. So a better way is actually to find the plane of symmetry of the sky plane velocity vectors. So we see these, we detect these objects, we discover KBOs because of their motion in the sky. And the projected motion on the sky, actually you want to be sitting at the sun and looking at that projection, that velocity vector projection on the sky. So think of this as a flow, like a fluid that's moving around of particles. And they have random motions, but they have some mean flow. Okay? So if you look for the plane of symmetry, that's going to be very close to or almost identical with the midplane of the Kuiper belt objects. So we want to look for the plane of symmetry. Now that's a little harder than simply doing an average of a few numbers to find a plane of symmetry. So we came up with a clever way of doing that. But very quickly I'll tell you why this is better. I think I already said it in words, but so this is a numerical experiment. If you take a bunch of random Kuiper belt orbit planes with a prescribed mean plane, and this is an example where we prescribe the mean plane to be 8 degrees tilted to the ecliptic with a particular nodal angle, and a dispersion around that plane of about 6 degrees, so plus minus 6 degrees standard deviation around this midplane. And then imagine a biased observation through this synthetic sample. So you're going to take your telescope and find all the objects that are in the ecliptic, within a few degrees of the ecliptic. Okay, so this is the red ones here are our experiment. So this is our intrinsic synthetic sample. This is what we say, we pretend that this is what we actually observe because we are confining ourselves to our telescopes, looking at only plus minus, I think it was 5 or 6 degrees, plus minus a few degrees from the ecliptic. So this is the sample we actually observe. Okay, so now if we find the average, so we can do this experiment many, many times and ask what kind of average we can come up with for this sample. How does it relate to what we know is the actual midplane, and what kind of dispersion and so on we can get. So we do this many times, and if we do that, so here was our experiment. That green dot is what we prescribed. If we take the average orbit pole vectors of the intrinsic population, this is the kind of dispersion we get. Okay, so if we do random numbers, generate 1,000 random numbers, and do that 1,000 times, we'll get slightly different average vectors from our measurements of even if we had the entire population detected. So that's those black dots, that black cloud there is what we would get even if we had the best observations and best measured everything with a sample size of 1,000. Now, if we do a biased sample like that within a few degrees of the ecliptic and measure the average of the unit orbit pole vectors, we'd get this cloud. Okay, as I said, it's biased towards being closer to the ecliptic. So we would end up getting, if we do the average of the pole vectors we end up depressing our estimate of the mean plane. But now if we do the best, if we calculate the best fit plane of symmetry of the velocity vectors, we end up with this cloud of red dots, okay, which has a bigger dispersion, but it's centered at the plane that we prescribed for our population. So this is a good way, this is a much better way of getting closer to finding the midplane of the Kuiper belt. So we did that with our sample, and we sliced up our sample in semi-major axis bins. These are the sample sizes we had, and we measured the midplane of these of our sample of KBOs at different mean distances from the sun. And indeed, for some part of this population, the midplane that we measure corresponds to what we expect theoretically. So this is these are so within about 50 astronomical units. Our measured midplanes are consistent with the theoretical expectation. But when we go beyond, when we look at the sample that's beyond 50 astronomical units out here, we get inconsistent answers from the measured midplane. So the measured midplane of the farther away KBOs is tilted by about 7 degrees, 7 plus minus 4 degrees, and it's at better than 97% confidence level. It is very distinct from the theoretical prediction, okay, by quite a lot. This is enormous, okay, by standards. You can see here, for example, we measure the midplane of this is mainly what we call the classical Kuiper belt objects, and the measurements are in really good agreement with the theoretical expectation. But here they're far away from the theoretical expectation. This is huge, a huge deviation from the expectation. This is some attempts to visualize what this means. So the midplane is kind of warped. So closer in, it's close to the midplane of the solar as expected, and then it's tilted away. Okay, so it's like the Kuiper belt has a midplane that's tilted away from the midplane of the solar system. So how do we account for this anomalous tilt? Well, these are some possible explanations. It could still be sample bias. That's parts that we haven't understood, maybe. Parts of or biases in the sample that we haven't identified yet. Could it be that since many of the more distant Kuiper belt objects that we know are in the scattering population, objects that have had scattering events, gravitational scattering by the giant planets, particularly Neptune. But if you think about it, so that's an easy thing to imagine. Oh dear, how late am I? Okay, I'm running pretty slow here. So if you think about it, scattering of Neptune is not going to it's going to produce an inclination dispersion, but not a change in the midplane, because there is Neptune. If you imagine just the sun, Neptune, and test particles, there's no other preferred plane in that system, but Neptune's plane itself. So scattering will produce dispersion, but not a midplane tilt. One thing that I think we should really keep this in mind is that perhaps a passing star or an impulse perturbation could cause perturbations to the outer parts of the solar system that take something like on the order of 10 million years to be erased. And that seems unlikely, because we don't have such frequent and close-in encounters with passing stars. But our solar neighborhood is not fully mapped out, really. So small stars, M stars, little red dwarfs, the density of those is not particularly well known. So I think we shouldn't completely rule this out. But another possibility is an unseen planet. So what kind of planet could produce this? So a planet in the same distance range as these KBOs, so beyond 50. So most of the sample we have of KBOs is in this range of 50 to 80 astronomical units that we can use to measure a midplane. A planet in this distance range can change the forced inclination vector. This would be a planet on the order of a Mars mass and up. So somewhere on the order of Mars to Earth mass can change the forced inclination vector to what we measure, to about the size we measure. If it's tilted, it has to be tilted to the midplane of the solar system. And that's our best guess, at somewhere on the order of Mars to Earth mass in this range, somewhere between 50 and 100 astronomical units, and tilted to the midplane by something on the order of 10 degrees. I should point out this is different than Planet 9 that's been in the news a lot, and so we'll talk about that. Figuring out what we can really do with the midplane is constrain this combination of mass, inclination, and orbit radius of the sky. So there's 3 parameters, and we have 1 constraint. So it's not a fully resolved set of parameters. And so this is a graph showing us the combination of inclination of the planet, mass of the planet, and its orbit radius, and what kind of forced inclinations it can produce with those different parameters. The other thing to note here is that such a planet would actually be quite bright. In visual magnitude, it would be around 15, 16, very easily observable, detectable by modern telescopes. Okay, so this is the conclusion for the midplane. This is our artist's notion of what this would look like. There are other arguments. So Silsby and Tremaine recently wrote a paper with numerical simulations of putting planetary embryos that were scattered into the Kuiper belt, and to account for these detached KBOs that I told you about. Okay, so these KBOs that do not approach the sun closer than about 40 astronomical units, 35 to 40, and those are very difficult to understand. Their orbital dispersion is very difficult to understand in the context of the known planets. And so these simulations suggest that something like a Mars to Earth mass size 1 or 2, 2 or 2 to 5 such objects scattered into the Kuiper belt could account for those detached objects. And this idea has been around, similar ideas have been around for the last 20 years or so, to account that these detached objects are a problem, that we don't understand their context well. So they are anomalous. What about other anomalies? This is coming to Trujillo and Shepard in 2014, noticed 2 things about the most distant Kuiper belt objects, these extreme Kuiper belt objects. These are the objects that have perihelion bigger than 40 and semi-major axes bigger than about 150 or so. So those are kind of arbitrarily defined boundaries, but they make sense in the dynamical context. So they noticed 2 things about this population. One, there was a gap in the perihelion distance. So we see these extreme Kuiper belt objects that have these large semi-major axes and perihelion distances above 40, but we don't see a whole lot of them in between about 50 and 75 in perihelion distance. And then they also noticed this other thing. This argument of perihelion is concentrated. So this is an angle which goes from 0 to 360 or minus 180 to 180 here. And this is this angle that only celestial mechanicians love. It's the angle between the nodal line and where the pericenter of the orbit is. Okay, so we measure this angle in the plane of an orbit, where the orbit plane crosses our reference plane. So this is this angle here. This angle, they noticed that this was kind of clustered around 0. Okay, around 0 meaning what? What was the reference plane? They measured it relative to the ecliptic. Okay, so they found that this was clustered, and they hypothesized. They did some numerical simulations and thought that they could tell that a planet, a super Earth planet, 2 to 15 Earth masses is what they suggested, at 2 to 300 astronomical units might account for this clustering, but not necessarily for this gap in perihelion distance. Then Batagan and Brown, 2 years ago, wrote this paper. They noticed 2 additional things about these extreme Kuiper belt objects, that their perihelion orientations were physically clustered like this. You can see these, at the time there were about half a dozen of these extreme Kuiper belt objects known, and their long axes, the long axes of these ellipses, are in this half or less than half of the circle. Okay, so they're clustered in this fashion. And the other thing they claimed was that the orbit poles are also clustered. So these little lines here that you see, each of these is one of these extreme Kuiper belt objects. The orbit poles are kind of clustered also on the celestial sphere. And then they multiplied the probability of those two things happening and said that the probability of both those two things happening was 1 part in 10 to the 4. But if you think carefully, those two numbers are not independent. If you have an orbit plane, its orbit pole is normal to the orbit plane, so you can't simply multiply those numbers. But nevertheless, it's a low probability. And they did extensive computer simulations to figure out what would be the parameters of a perturber of a distant planet that would produce this kind of clustering. And they came up with this grid, which is the same major axis and eccentricity of the planet. And each of the numbers in this grid is the probability of success in meeting those metrics for accounting for these clustering, these orbital clusterings. And so they came up with this set of parameters as their preferred parameters for the orbital, for the mass of about 10 Earth masses, orbit of about 700 astronomical units, which is on the order of 20,000 years in orbital period, an elliptical orbit inclined about 30 degrees, but unknown location within the orbit. We don't know where the planet is within the orbit, because all it does is cluster the shapes of the orbit. So it's like you can identify the parameters of that elliptical wire, but you can't say where in that ellipse the planet is located. And you can see the numbers here. So I put this up because these numbers are small. The probability of success they have is actually not especially impressive. It's a few percent success in different parameters. There's no particular reason to favor this set just looking at this grid. I think they convinced themselves that there were better reasons for this set rather than any one of these with the non-zero numbers. Okay, so this is the range that helps you get that clustering in numerical simulations. Added to this was some really interesting points made by a few people, Bailey et al., Dong Lai in Cornell, Gomez in Brazil, that if we had a large planet like this at a large distance, it would dominate the total angular momentum budget of the solar system. Okay, so this big lever arm provided by a 10 Earth mass planet at 700 AU, you can then ask, what does it do to the rest of the planetary system, to the orbits of the other planets over the age of the solar system? And actually the planets, all the major planets will precess like a rigid system, but not so the sun. Okay, so the sun's tilt, which is about 7 degrees to the mean plane of the solar system, so it's about 6 degrees, 7 degrees to the ecliptic. It turns out that if you have a planet like this, it can actually account for, after precession for 4 gigayears, if you started this planet or started the planet's coplanar and then ejected this guy into this orbit, into this inclined orbit, over 4 gigayears, the sun would be tilted about 7 degrees. Okay, so that's really attractive. We now have the first explanation for why the sun is tilted, or first more credible explanation. There have been other attempts at that. Another piece of work that was quite useful and important, Fienga et al., this is I think at the Nice Observatory. They calculated, they looked at the position of the Cassini spacecraft and asked, look at the very precise location that we had for Cassini and ask, would the orbital perturbations, would the perturbations from this distant planet improve our understanding of how Cassini was moving? And what they did was to show that you could rule out within the orbit, this preferred orbit that Batakian and Brown came up with, within that path, you could rule out that the planet could not be in this range or near perihelion over the red and pink parts would produce too big a perturbation to account for Cassini's path, but you couldn't rule out the rest of this orbit. Okay, and then Holman and Payne have written a couple papers looking at this again, as well as looking at the astrometry of Pluto and other other TNOs, other KBOs. And they can rule out most of this orbit now. So you can allow, planet 9 is now confined to being way, way there at aphelion. Any other place, and actually you need even a bigger orbit to allow it. And they find that it's of marginal significance. All of these data are consistent with no P9, but you can't completely rule out P9 near aphelion at large distances on the order of 1,000 astronomical units at its aphelion in this orbit. Another one I should point out is this paper last year by Shankman et al. This is the group in UBC. They've been doing probably the most systematic survey, observational survey for Kuiper belt objects. I think they account for 20 or 25 to 30% of all KBOs that have been discovered. They pointed out that in their survey, there are these biases in the discovery of objects that have perihelia, these argument of perihelion, node angles, and the longitude of perihelion, the way the ellipses are directed. That these are the systematic biases based on how they survey the sky. And many of their biases are common to all surveys, to all telescopes, because many of these are seasonal issues, telescopes that are clouded out or are clouded out by monsoons or the moon and so on. And so these are systematic biases, and they say that these are common to all surveys, and therefore the entire Kuiper belt database that we have has these same systematic surveys, and they happen to be just where that kind of clustering would occur, the clustering that Batagian and Brown and Trujillo and Shepard have noted. Now, Brown disputes that such bias exists in the combined survey of all, in the combined sample of all KBOs. So that's a dispute that's out there. So here's an updated version. So back then, 2 years ago, we had these ellipses that were all in this part. Now we have a few. You can see 1, 2, 3, 4 in the opposite hemisphere, or so opposite part of the circle, semicircle. So there's some eroding of that clustering. So one important point to make is that these new hypotheses are based largely on statistical arguments, the distribution of these minor planets' orbits, and computer simulations of a solar system model. They're not based on, for example, the classical, the way that Neptune was discovered, okay, looking for anomalies and accounting for the position, the exact mass and position of an unseen planet. Although if you really read the history of that, there was a lot of guesswork that went into predicting the position, the exact position of Neptune too, and to some extent Leverrier and Adams got lucky. All right, so notably the P9 hypothesis, I should mention, does not account for that perihelion gap, and also doesn't account for this argument of perihelion clustering that was originally noticed by Trujillo and Shepard, and we still don't have a good accounting of that. I've almost run out of time here, so I should very quickly tell you this paper that we wrote a couple of years ago. I got really excited about this, okay? So I lost a lot of sleep looking at all this data and the dynamics, and, you know, is there a planet? What else can we come to bear? First thing I noticed was that these half a dozen Kuiper belt these extreme Kuiper belt objects, their orbital periods are close to integer ratios with each other. Okay, small integer ratios with each other. And this didn't come out of the blue. The Batagian and Brown papers said that in their simulations they saw the reason for this clustering had something to do with orbital resonances with the planet. And I said, oh, okay, so if there is a planet, there should be resonances with that planet. And so I looked at so if there are resonances with the planet, then the period, even though we don't know where the planet is and what its orbital period is, if each of these KBOs is in resonance with the planet, then the ratio of the orbital period with the planet is a small integer ratio. And then if you take the ratio of two small integer ratios, you get another ratio of two small integers. So if you just take the observations of these extreme KBOs and ask what are their ratios with each other, so you can pick one at random. Let's pick Sedna, which happens to be the outermost one of them, and ask what are the ratios of the orbital periods of the others with Sedna, and that's what you come up with. Okay, they're pretty darn close to small integer ratios. And so we said, let's run with this and figure out what does this mean. What can we say, what can we guess for the orbital period of the planet? And it turns out if you just the first thing you can guess is, okay, let's look at Batagian and Brown's planet, somewhere in that range around 700 astronomical unit radius or semi-major axis. Somewhere in that neighborhood, the first thing you can pick up very quickly is that at 665, a planet at 665 astronomical units would produce these orbital period ratios with these 6 Kuiper belt objects. Okay, these are pretty tiny numbers, small integers, 3 to 2, 5 to 2. Now the orbits of these guys are not sufficiently well determined, so there are these error bars. So these are the best determined orbits, and there are error bars around those. And so it turns out that if you have a planet of mass bigger than 10 Earth masses, it produces a resonance over some width. And these error bars are small. The widths of the resonances are going to be bigger than those error bars if the planet's mass is bigger than 10 Earth masses. Okay, so then we can say these guys would be in resonance, and what can we do with that? Well, if the resonances are real, then we can say something about where the planet is in its orbit. Okay, not just what the orbit is or orbital period is, but also where it is in its orbit. And a simple analogy of that is we have this 3 to 2 resonance between Neptune and Pluto. Since we know where Pluto comes to perihelion, we can say that Neptune is not going to be in that location. Okay, it has to be about 90 the planet that's producing that resonance is 90 degrees away from where Pluto comes to perihelion. All of these extreme KBOs have elliptical orbits. Okay, so we can say something about where the planet is going to be in its orbit by knowing where these objects come to perihelion. Okay, and so we did that. There's geometry and physics of resonant orbits. What we can do actually is to rule out parts. Okay, so just like for Pluto, we could rule out where Neptune is because it has to be away from Pluto's perihelion. We can rule out parts of the planet's orbit for each of those resonances with each of those Kuiper belt objects. And this is a map of the sky, so RA and DEC, where the planet cannot be in its 17,000-year orbit, which is inclined 18 degrees. That 18 degrees comes from simply looking at the average plane of these half a dozen extreme Kuiper belt objects. But that plane is not uniquely determined. It turns out there's a sweet spot at 48 degrees, and this is again doing celestial mechanics. And one of the advantages, one of the things, the only thing I think that explains that one feature about the clustering of the argument of perihelion is having a planet at 48 degrees. Okay, that has to do with something called periodic orbits of the third kind in Poincare in the three-body problem. Henri Poincare identified these long ago, and so that's what we found in the analysis we did. So we can rule out some parts of the sky, and we can say that the planet can be at these other parts. Unfortunately, that still means looking at most of the sky. There's not a whole lot. And also, if you're an observer, are you not going to look here because I told you that the planet isn't? Okay. All right. Quickly, then the biggest new survey that's coming online is the LSST, the Large Synoptic Survey Telescope, and we did a little paper recently, and main point there is that both these planets, 10 and 9, will be readily visible if the planet is anywhere in that part of the sky that this telescope. It's mostly the southern sky. So that's 61% of the entire sky. This planet will be easily found in single frames if it's closer than about that distance. There's a little wedge there. You'd have to go to multiple co-adding of frames to identify it if it's farther than on the order of 1,200 astronomical units. Okay, I want to tell you about my collaborators. Most of this work was done with Kat Wolk, Shanyu Wang, and Lei Lan. Shanyu and Lei were visiting from China, and Dave Trilling up in NAU, and Eric Bellum. We did this recent paper on the LSST detectability of Planet 9. NSF, NASA, and the Marshall Foundation for funding. And here's my summary. I apologize, I've gone over time. I'd be happy to take questions or talk with you offline. Happy to talk. There's lots of interesting physics to be done here, and I'm happy to work with anybody who would want to work on this. Thank you.
Questions?
I was wondering, in the first part of the talk, you had a method for dealing with the observational biases, looking at velocities. I was wondering if you could apply that you did on planet 10, also for planet 9, because I'm worried about the observational biases in those extreme types of anomalies.
So Shankman's paper has done exactly that, but they did it for part of the Kuiper Belt database, their own survey, which is a good fraction of all the KBOs. Has anyone done that beyond that? So Mike Brown makes the argument that there is no such bias as Shankman at all. So you can look at those two papers. So they've tried to do that. To find specifically to look at the midplane of those is hard. With a sample of 12, it's meaningless to ask for the midplane to actually represent the actual midplane out there.
So you have two different possible planets, one pretty massive and pretty far away, and one still pretty massive, it's a little closer. How did you get those there, if they were there?
Yeah, so I tried to make that point there. So Silsby and Tremaine talk about these scattered embryos, planetary embryos. Okay, this was so scattering can produce that. Okay, so this is these are objects that are scattered that were formed closer in, somewhere in the range of Jupiter to Neptune, and they are scattered by the giant planets, go into bigger orbits, and if there's enough of them, on the order of a few of Mars to Earth mass objects, their mutual scattering will push them out, will lift up their perihelia over time, right? So that's feasible for this P10, I'd say, for the one that's closer in. To get something out at 10 times Neptune's distance, this doesn't work, and there's physical reasons for that. The upper limit to scattering this is roughly around 300 astronomical units. To get a planet out at 700 is much harder, much less probable. So this mechanism doesn't work for P9.
Does that mean, though, if your P10 is right, that it has to have some friends?
Yes, so very improbable situation would be to have a P10, a few P10s, and a few P9s, and they mutually scatter and somehow produce, lift themselves up, bootstrap themselves up. But it's very, very low probability of doing that. Yeah. Yes, way back in there.
For P10, you mentioned the visual magnitude could be something like 15, 16.
Yes.
Was that assuming the same Earth composition? I would think that something like 100 AU rocky composition would be great.
Yeah, so in that, yeah, I actually had that combination there. And we discussed that in the paper. So this is a V of 15, and for a certain assumed density of the planet, which gives you a certain size. So given the mass and a density, the visual magnitude is, so at low density, like 2 grams per cubic centimeter, would give you a visual magnitude of 15 for a 1 Earth mass object out at about 100 AU. If it's more dense, it would be a little bit brighter, because it would have to be a little, did it go the other? Yeah, that's right. Okay, so it's in that range. So slight variation. Densities aren't going to change by an order of magnitude. They'll change by 50%, 100, factor of 2. So it's this is a pretty good estimate for the visual magnitude.
So similar question. I mean, we've surveyed a lot of the sky already up to that magnitude. So there's been lots of these things showing where we would have found P9 already.
Mm-hmm.
What fraction of the sky would we get P10?
It turns out to be there's lots of sky that hasn't been covered. And the reason is, sure, we've surveyed practically all of the sky, but we haven't looked for the motion of bodies. Okay, so it's that looking for that motion. So the same part of the sky has to be surveyed in a certain period of time to look for changes in position. That hasn't been done for most of the sky. So a good part of the sky hasn't been done to this magnitude.
So the implication is that you have data out there that could potentially reveal.
Yes, it's probably sitting in. It's like Uranus that was found in older data. It's probably sitting in somebody's, maybe in your data.
What kind of speeds are we talking about for the planet?
The sky rate of motion. Yes, I had a figure for that. Let's see. It depends on the distance, and if it's in the range of 100 AU or so, it's on the order of 1 arc second per hour. Okay? 1 to 2 arc seconds per hour. Farther away, it gets to sub arc seconds per hour. Out at 1,000 AU, it's a tenth of an arc second per hour. Yeah, just goes as 1 over r to the 3 halves. Yeah.
It's a very slight motion.
It's a small motion. Yes, you're used to asteroids, so just for context, asteroids move at what, 100 or 200 arc seconds per hour, right? Do I have that right? I just did that. Yeah. Okay. Yeah. So asteroids are you're spoiled. Yeah.
So after all of this, what would you say the likelihood is that these planets exist?
Very marginal statistical significance for all the data we have right now, but it's very intriguing. It's multiple lines. They're all low probability, marginal. All the resonances, I should have mentioned. The resonances, if you take 6 numbers, 6 rational numbers, randomly, they are not unlikely to fall close to these small integer ratios. So I did that calculation too, and it's not a probability that you can totally dismiss. It's just of marginal significance. Yeah.
And to move you a little bit outside of your comfort zone, maybe, thinking about if there's a Earth or Mars-sized body at 50 AU, what would the surface look like? What would you expect geologically for a body like that?
So people have been making these models for exoplanets. I haven't seen any artist renditions of that. Has anybody seen those?
Kind of fun to think about, right?
Yeah. So here this would be, well, if it's a 10 Earth mass object, it would be more like Neptune. I think there's not much to imagine there, but something like an Earth mass or 2 Earth mass at 100 AU, which is icy, would be, well, I don't know, super Ganymede?
One last question.
Just to add to that, I mean, one of the things that came out of the Pluto encounter was Sputnik Planitia, where we have this convective nitrogen sea, and Will Grundy has, questioned whether some of the bodies may in fact have, nitrogen oceans, which are convective, and that's actually kept fairly fresh and bright. And so with something the size of an Earth mass, you might have enough geothermal energy to power, convection of these cryogenic ices. So it might be actually fairly.
That's true, yes. So Pluto has been quite surprising. These lower temperature ices could actually be geologically active in a bigger body, more active than even in Pluto. So it could be a very interesting geological body. And it would be a window on planetary embryos in the outer solar system. So we think that the giant planets were made out of, the giant planet cores were made out of accumulation of these planetary embryos. So this would be really remarkable if we were to find it as a leftover planetary embryo, a hugely useful window into planet formation in the outer solar system. Yeah. But yes, it could be geologically active with these low temperature ices.
Okay,